In this video, we are going to see about armature reaction in an alternator. Okay, so when an alternator is running at no load means there will not be a current flowing through the armature winding. Okay, the flux produced in the air gap will be only due to the rotor, that means rotor ampere turns. But alternator is loaded now. The three-phase current will flow through the windings of the armature. So once the current is flowing, whenever a current flowing in a conductor, and flux will be established. Okay, so now here the current is flowing through the alternator armature, so that the current is flowing, so that the flux will be produced. Since it's a three-phase current, right? So since it's a three-phase current, a three-phase flux will be produced. That is nothing but a rotating magnetic field. The resultant is nothing but rotating magnetic field. As like induction motor, whenever a three-phase supply is given to the balanced three-phase networks, a rotating magnetic field will be produced. Okay, so now we'll see what happened here. So here there are two flux. One is due to the rotor, that is we call it as a main flux, and second one is stator flux, that is nothing but an armature flux, that is due to the current flow under load condition. So the two fluxes are fixed in space relative to each other. Since the rotor also rotating with a synchronous speed and stator also rotating in a synchronous speed, so the two fluxes fixed relative to each other, so that there is a modification of the flux due to the amplitude and the power factor. Okay, so the armature reaction is nothing but the effect of armature flux on the main flux affecting its value, and the distortion is called armature reaction. So the effect of armature flux not only depends on the magnitude of the current, but also depends upon the nature of power factor. So because here the alternators feeding the power to the external loads, so the current is flowing towards outside, right? So the loads may be any kind, so resistive, inductive or capacitive. So according to the load pattern, the power factor also changes. According to the power, the effect of the armature also differs. Okay, so that we will consider here three cases. One is load under unity power factor, and load under zero lagging power factor, and load power factor and zero leading power factors. Okay, so the three cases we will be considering here. So before we talk about the armature reaction, we'll see the few facts here. So you see here, this is stator and this is rotor. Okay, so if you notice here, the rotor is rotating at a synchronous. You consider here only two pole rotor, so north and south pole. Okay, so if you see here, there are three conductors, that means three-phase conductors are placed in the slots of the armature winding. Now both are rotating in the synchronous speed. So you have to notice here it's a three-phase current, so that the three-phase current with the 120-degree phase will be flowing in the currents. So once the three-phase current flows, definitely the flux will be produced. So here we have considered two poles, so that the flux is also consider two poles. The fluxes also will be a two pole. For example, if you notice here, this IA, it is a maximum. In that case, the A and the B dash and C all together will be a inflowing. That means the current flow through the conductor towards inside. And if you see the bottom, C, A dash and B will be outgoing currents. So as you know that the current flowing inside, we will make it as a cross, and the current flow through the outside will make it as a dot. So the cross will produce a north pole and dots will produce a south pole. So this is the condition. So the resultant flux will be 1.5 times will be the resultant current. Okay. In the next case you consider IB. So IB is here the maximum, the B phase voltage is maximum at this case. In this case you have to notice here, so the direction of fluxes also will change. That means the poles, north pole and south poles will change. So here now these three will be in the north pole side and these three will be in the south pole side, so that the direction of rotating magnetic field also changes. That means the direction of north and south pole also changes, but the resultant is same. So similarly for the current IC also, if you notice here, so the flux is rotating in nature, but it has a constant value. Okay, so this is the first fact. Second thing, the pi is nothing but a pi m sin omega, whereas pi m is nothing but a maximum flux, sin omega t is the rotating field. E is nothing but a EMF developed, that is EMF induced here equal to change in flux to the change in time. So E equal to, if I take a derivative, E equal to pi m cos phi. The EMF is always 90 degree lags pi f. That means the EMF lags the 90 degree of the main flux. So now consider two figures. The first figure is talks about the rotor flux direction. The second figure talks about the armature flux direction. So if you see here, the north and south pole, the current is flowing in the middle of the north and south pole. The winding is made in the middle of the north and south pole, and so that the flux directions will be towards the 90 degree opposite. Okay, so here if you notice, the flux direction is given in this. That means now in this condition, the first condition, that means the first figure, the stator is not energized. That means there is no load, so only the rotor is energized, so it produces north and south pole. The direction of flux is shown here. But the second figure, you notice here, we are not considering the rotor excitation. That means the no rotor excitation. Okay, so only the stator is flowing the current. Okay, that means it's not showing the direction of flux. It is excited, but it is not showing. The rotor is excited, but it is not showing the direction. Only I am showing the direction of armature flux. So if you notice here, in this case, the first figure, the main flux will be in this direction, the EMF will be 90 degree lagging. Okay, but in this case, that means the second figure, it is depends upon the direction of flux, depends upon the, this is armature flux, this is depends upon the direction of current. Okay, so the current direction determines the flux direction. Okay, now we'll consider three things. Unity power factor. First we'll consider unity power factor. Okay, now in unity power factor, it is a pure resistive load connected to a alternator, so it's having unity power factor. Okay, as induced EMF, that is E phase, drives a current of IA phase. Okay, here I have considered only the armature current IA phase, and the load power factor is unity here. That means the E phase and IA armature current both will have a same phase, so that the flux direction also in along with the IA, so that the E phase, I phase and flux direction of armature pi A will be in same direction. The main flux, if you notice here, that is pi F 90 degree lags here, 90 degree leads here. So the E phase or the IA lags 90 degree by the main flux. Okay. So now you consider here, this is the conductor. I am considering only two conductors here. One is cross, another one is dot. Okay. So you consider here two poles. One is north, another one is south. Okay. So if you notice here, the direction of flux in a conductor, that means a cross conductor, will be a clockwise. If you see here, the direction of flux in the dot will be anti-clockwise. We know the direction of north pole, so usually the flux flow from north pole to south pole, so the direction will be in this way. This is north pole, so the direction will be in this, and here similarly the south pole, the direction will be here. If you notice in this two figure, the direction of flux, one point it is aiding each other, in another point it is opposing each other. Similarly here also, here aiding, here opposing. So if you notice, the resultant flux will be like this. So this is the this is the green one is the armature flux, the green one is the field flux, the dotted line is the armature flux, this is yellow line is the resultant flux. So if you notice here, this half from here, the resultants, if you notice here, this is the resultant, these up to this it is opposing. So from here to this, both are aiding. So if you see here, the general neutral point should be at this position, but the resultant is now little shifted here. So resultant is now shifted at this point. So the 90 degrees shift is there. So the effect of this one will be a cross magnetism. So if you notice, one point it is aiding each other, another point it is opposing each other. But if you notice, there is the total average flux, that means one point adding, another point it is decreasing. The total average flux in this point will be same. So there is no decreasing or demagnetizing effect. So only here distortion effect is there, that is nothing but a cross magnetizing is there. So hence such a distorting effect of an armature under unity power factor condition of a load is called cross magnetizing effect of an armature. So due to such distortion, there will be some drops in the terminal voltage of an alternator. Now we'll see